friends, today I want to show you how you can use Famos script functions to automatically generate the trajectories needed to pick and place these little boxes. As you can see, we have a single robot, a gripper, a pallet, and a number of boxes. Simple CAD models following a special name convention. They always have the same name with a number at its end. Okay, now the task is to create a script and automatically generate the trajectories, these ones, to pick the boxes and place them on the pallet. Each move is basically an approach, the pick operation, and a retract operation, and then the place operation with an approach, place, retract. And the informations we have is that the project comes with 10 boxes named like this. Okay. Let's delete the palletizing program and open the script. The script in this case is part of the project, and if you open the project folder with a double click in the status line, you can find the script. It has the same name as the project and is stored in the same folder. We drag it simply to the Famos main window, and immediately the script editor opens up and shows the script. Okay, about scripts. Scripts in Famos are based on a subset of the Pascal language, a very popular language in education. There are tons of resources, sample codes out there in the internet, and we have added, I think, 20 or 30 sample scripts for many tasks. And this one is part of a sample project that you can download from our web page, and it starts here, the main routine. We have for the palette a grid, and you can define the grid dimensions on the palette here. And then we call the palletize function. That starts here. First, we initialize some variables that indicate where we have placed the last box in the grid of the palette. Then we check is the required project loaded. We identify this by asking for the existence of some frames, the gripper, a work object, a base coordinate system for pick and one for place. That's very basic stuff. You have a function, a return value with a type of Boolean, a list of local variables. The type is tObjectID, and then you can access functions of the Famos robotic API. Those functions will always start with FA underline. And if you open the integrated programming help, you can easily access all API functions. It's a lot. It's a very powerful API which gives you access to all geometric objects, to all parameters, and the project itself, and others. Simulation, collision control, everything. Okay. So we call an API function asking for the existence of a TCP called TO_gripper. And if it returns with a non-zero value, then this object exists. If the gripper and the basis exists, we start the palletizing. Our sample creates a single new path for all the parts, and then we run through the parts. The names are have an index at the end, and in the function getPartID that retrieves the index as a parameter, we get, where is it? getPartID, here is it. We ask for the cut model ID, the cut frame ID, with this name, the part name prefix, that is this one, and the part number. I think you recognized you can easily add more boxes by duplicating them and add a number at the end, and then you can increase the number of boxes or decrease the number of boxes in the project. And of course you can arrange the boxes in the cell like you want. So nothing is fixed. Okay, let's continue the palletizing function. We create a new path, then we iterate through all the parts, and then we get the bounding box of each part to get the dimensions. Then we ask for the grab position for the part. That's a self-implemented function. And it is, where is it? Here is it. We have the frame of the cut model of the box. As a programmer, we know where the frame origin is, and with the information about, here's a frame origin in the center of the box, exactly in the center of the box, and with the bounds we can calculate a position on the top, and that is our grab position. And that is what we return here in result. As you can see, we can ask for the transformation of a coordinate system relative to any coordinate system in the scene. We can perform all basic mathematical transformations for the matrix, like a translation relative to the local axis of the coordinate system in this case. And then we return the matrix as a result. And this result is passed to the function at pick targets. First we grab or pick the box, and this is done here. We get the pick matrix, that is the position on top of the box, base and tool ID, part ID, and the bounding box of the part. And then we create a matrix from the pick matrix and height of the model of the box. And then we create a target with this information and apply some parameters. like zone and speed. For the approach position, we don't use the find position, we use a position with a TCP zone radius of 10 millimeters, and it's a high speed point that we're trying to reach with 1,500 millimeters per second. The next target, that was the approach calculation. Then we have created the approach target, and then we create the pick target and set the pick parameters, and then the depart target with the approach parameters. We simply use the same. You can use any parameters of your choice. Okay, the pick parameters are special. Here we access a parameter pick object value and pass the part ID. We set the zone radius to 0 to get a find position, because we want exactly reach the target. And we do this with a reduced speed of 150 millimeters per second. Yeah, and basically that's a picking, and the next step is we have to place the box on the pallet. That's a bit more to calculate. Here we calculate the cell index on the pallet, X and Y grid position. The spacing between the positions depends on the boundings of the part, delta X, Y, and Z, and then we create our transformation for the place operation. That's similar to the pick positions. The difference here is we set the place parameters, the place object value set to part ID, zone radius 0, speed reduced. And all this is executed in a loop, and a while loop, until we get no more part IDs from get part ID. Yeah, that's basically the script. And now let's try it out, check it out. The script is, the path is deleted, and we simply execute the script, and that's it. It's very, very fast, isn't it? And then we can simulate it. Pick and place. All this is very basic. You can add more advanced features like automatically detect the order of the boxes to pick depending on their geometric location in the cell with respect to the robot. In this case, it's simply done by the number of the box. You can run collision checks, whatever. By the way, I can stop this here. If you want to relocate one of the boxes, try another position. Let's try box number 1. Box number 1 is this one here. We move it a bit to the right. and up. Why not? And back. Why not? Okay, then we have to reinitialize the initial positions for all the boxes, and then we have to recreate the script. Let's check that out. The old path will be removed with the new one automatically. So if you make any changes in the script or in the cell and have to re-execute the script, you can simply do it by by hitting the play button for the script. You don't have to delete the previously created path manually. Okay, hope you enjoyed it. Have fun to play around with it. Don't forget to download the sample project from our demo download page on famosrobotic.com or .de. Thank you very much. Goodbye.